Hello chat, today we have some amazing Pearl Harbor physics. Yes. Okay, so table of contents, we're just going to talk about the bomb, torpedo, and then some AAA. So this is the disclaimer. I'm taking stuff from Wikipedia because I'm lazy, but some of the stuff I have cross-checked with other people and other sources, and I'll try to show my work and state the possible errors in the video. And I also don't care about sig figs because I put however many sig figs I like. Okay, so number one, we're going to be talking about bomb. So some of the B5Ns had these 800 kilogram bombs that weren't actually bombs. They were modified AP shells that were meant to be dropped from a high altitude, and then that would pierce the deck of the ships. So according to my equation, they landed at 337 meters per second in about 25.2 seconds, and which means that air resistance slowed down the bomb by 7.7 meters per second only, which would make sense because the bomb is meant to be aerodynamic so that the air doesn't slow it down too much. And if you plug those numbers into the kinetic energy formula of half mv squared, you get that the bomb landed with a kinetic energy of 22.5 millijoules. And here is the reference I'm using. Yeah, it's a converted 40 centimeter AP shell, so keep that in mind. So here's my work. We're going to be using this equation, which is my equation that I made with a couple of friends, which I'll explain in a future video, hopefully. So height is going to be 3,048 meters. Everything here is in metric units, so no disgusting feet or pounds or whatever. Okay, so it's 3,048 meters. That's the bomb drop height. And then the the area of drag is 0.04 pi because I just assumed that the bomb's drag area was a circle which has an area of pi r squared. And r squared is what we need to find out. So r is kind of here because it's a 40 centimeter AP shell, so r would be 20 centimeters. That would be 0.2 meters. And then 0.2 meters squared, which is r squared, would be 0.04, hence why the area is 0.04 pi. And the drag coefficient, I could not find anything regarding the specific drag coefficient of the bomb, because I genuinely don't think they would test something like that. So I just took it from the closest thing I can find on analysis, which is the bullet, so 0.295. This is probably very erroneous, but hopefully it's close to the real time that it took the bombs to drop. Again, I'm just theorizing. I don't know much real data here. And the mass is 800.14 kilograms, and the air density is taken to be 0.9, but we all know that air density kind of varies with altitude, and yeah, this density here is taken at when the bomb was dropped. So the air density is going to get denser as the bomb goes down, so technically I think the bomb should actually land a bit slower than this number here and have less energy than stated here, which means that this time will also be bigger and that the air would have slowed it down more. Okay, so here's the graph. This is from my equation here. Yeah, so as you can see, this is a height and height time graph. I think that's what it's called. So the velocity at 25.2 seconds is 237 meters per second, and the height is 3,048, which pretty much matches the Wikipedia equation on freefall with air resistance that I've inserted here. Yeah, so as you can see, the numbers are pretty much the same. Actually, they're exactly the same. So, yeah. Okay, number two, torpedo. Okay, so the torpedo equation, basically, torpedoes, when you drop them, they roll. They kind of spin on themselves. And we can make an energy statement for that. So, basically, the what is called the potential energy is equal to the kinetic energy plus the rotational kinetic energy. So when we plug in the appropriate terms, 838 being the mass of the torpedo, 9.81 being the gravitational acceleration of the Earth, and we plug in mass again here, and the specific the specific rotational inertia of the torpedo when it spins around its center is going to be 0.5 mr squared, which I have taken from this diagram as a reference here. And the other trick that you need to know is that velocity is equal to the rotational velocity, or omega here, multiplied by radius. So that means that omega can also be velocity divided by radius. So moving on to this line here, we just multiply these two numbers out here, multiply those two numbers, and there's a r squared on the top here, and then there's a r squared on the bottom here, so naturally they will cancel each other out, so you're just left with 0.5 m and then v squared. So once you have that, we're going to multiply the two 0.5s here out, and then we get this, and we insert m back in, and we get this equation here, and when you add them, you get this last line here. And when you separate v on one side, you get this as the final result. So the velocity that the torpedo landed in the water with is proportional to the root of the height that it was dropped from, multiplied by 13.08. And then finally, AAA. Okay, so I've just taken Helena's Wikipedia page and just checked some data on it. So according to her Wikipedia page, she fired 375 5-inch shells, I think they were DP guns, 3,000 1.1-inch shells, and 5,000 .50 cals. So as you can see, I've listed the properties here. So this is not that hard to find. I mean, anyone can do a kinetic energy calculation with these numbers given here. So it said the 5-inch shells would weigh anywhere between 24 to 25 kilograms. I didn't know which one to pick, so I just picked an average of 24.5 and used that in this calculation. And I don't know the mass of the 50 cal bullets, so I couldn't actually do a calculation of those, which is a bit unfortunate, but I'm too lazy. I mean, like the whole Wikipedia page for the 50 cal is like 2 million pages long, and I don't want to read through that. So yeah. Okay, so if we multiply the energies that were given on the previous page, we multiply that by the amount of shells that were fired, we essentially get like 3 gigajoules for the 5-inch shells and 420 millijoules for the 1.1-inch shells, and that adds up to a total of 3.3 gigajoules of energy. And there's actually going to be more energy because the 5,050 cals weren't taken into account. So the total is going to be more than that, which is why I put a plus here. And yeah, that's it.